Hello everyone, welcome to our discussion of section 7.3 where we will be talking about calculating volumes using cylindrical shells. Now in the previous section we talked about calculating volumes using the washer method and the disk method. So this would be a different method because sometimes we have expressions that are volumes that are too complicated to calculate using disk or the washer method. Specifically, we're talking about cases where it is very difficult to write a function in terms of x. So you see two examples of it here. So we have these two functions given in terms of x, but we want to, let's say we want to write these in terms of y. If we wanted to write this function in terms of y, we would have to solve for x, right? And that would be very difficult or not even possible. So the same thing here. How would we have the function given in terms of x and we want to write it in terms of y. In other words, if we wanted to solve this expression for x, how would we do it? So it would be a complicated procedure. So in such cases, we use the cylindrical shell method to find the volume when we integrate. So the question is then, how does this method work? The cylindrical shell method work? So given that we have a continuous positive function, let's call it f of x, then this is the formula to use with respect for the cylindrical shell method. So a and b, as usual, they represent the limits of integration, 2 pi, because it's a cylindrical shell. So we have 2 pi, and then the radius of the shell, and each of these we have to talk about when we get to the next slide in terms of what they represent. So radius of the shell and times the height of the shell. So this would represent the volume, and then integrated either with respect to the x variable or the y variable. So that dx or dy is called the shell thickness. Now, there are a couple of important notes that we have to be aware of right from the outset. First, the shell is always constructed such that its height is parallel to the axis of rotation. Just remembering this helps us a lot in determining how the integration should happen. The limits of integration, the radius of the shell, all of that depends on construction of the shell. And the construction of the shell is always parallel to the axis of rotation. So if the axis of rotation is y, then the shell has to be constructed such that the height of the shell is parallel to the y-axis. The other important note that we ought to be aware of right from the get-go is that the radius of the shell, right? So we're talking about these two components of the formula. Now this one, the radius of the shell is the distance from the center of the shell's height to the axis of rotation. Both of these, if we forget these, we won't be able to integrate. Okay, that's very critical to determining what goes here. All right. So the next slide, as I promised, talks about geometrical interpretation of the height of a shell and radius of a shell. So let's call this case 1. If we're rotating a cylindrical shell about either the x-axis or some other line that is parallel to the x-axis, and I have that picture here where we're going to be rotating, this is the symbol for rotation here, this arrow. So here in the bottom picture, we're rotating with respect to a line y equals -5, which is parallel to the x-axis. But here, we're rotating about the x-axis itself. Okay? So, how does then the shell height, because we're rotating about the x-axis, the shell height, as the note on the previous slide mentioned, the shell height should be constructed parallel to the axis of rotation. Axis of rotation in this case is x, denoted by this arrow. So the shell height is parallel to the axis of rotation. Now, if the shell height is parallel to that, what is the shell thickness? In this case, it would be that thickness of the shell you see, that tiny thickness. And that thickness is along the y-axis, right? So we know in this integration, we'll be integrating with respect to the y variable. Okay, so all of that is tied together. The parallelness of the shell height and the thickness of the shell, dy, and shell height, that would be with respect to the shell height would be with respect to the f of y. Okay, so that would be x equals something, right? This is one of those cases where we have to write x in terms of y. So that would be that. And then the shell radius would be the distance, as it was mentioned on the previous slide. It would be the distance from the center of the shell to the axis of rotation. And that distance is simply y. So we have 2 pi in front, as we had on the previous slide, right? 2 pi is always present. 2 pi times radius of the shell, in this case, radius of the shell is the distance from here, any point on that blue curve to the axis of rotation, which would be represented by the y itself. And then the shell height would be this distance along the x-axis, or parallel to the x-axis, right? For every point on this curve, the shell height will change according to the distance of that point from the y-axis, which is the x value, right? So we would have x equals something, and we would integrate that, and that would be this function, f of y. Okay, so now that was when we have rotation about the x-axis. What about if we have rotation about an axis that is parallel to the x-axis? This one, right, denoted by this semicircular arrow. So for that, again, the 2 pi is already present. By the way, here, up here in the previous exam figure, the limits of integration in this case are taken from along the y-axis, but from 1 to 5, and that's 1 to 5. Okay, so here we have the same limits of integration from 1 to 5, and the 2 pi is there, but this time we have rotation happening along an axis that is a distance away from the x-axis, right? So in such cases, radius of the shell is the distance from the center of the shell to the axis of rotation, right? That's the definition we gave on the first slide. Now that distance, the distance between two things is always a positive measure. So never mind that this is y equals -5. The distance is going to be positive. So we're going to have y, which would be the distance of that center of the shell to the x-axis. That would be y, right? But we have an additional distance down from that, so that would be y plus 5. That's why you see y plus 5. Again, this distance is always positive. So we're not going to write y minus 5. It's just y, that distance y, plus an additional measure here. So if y was, let's say, -3, that would be y plus 3. If this was y equals -7, that would be y plus 7. Okay? And of course, the shell height shell height is because the shell is parallel to the x-axis, then the shell height is the distance from any point on the curve to the y-axis. But what is that called? That's x value, right? So if this was a real example problem, we would have to write x in terms of the variable y and then plug it in here. Okay, so that would be that. So this is just laying the foundation for this before we get to examples of this type. So we talked about rotation about the x-axis and another axis that is parallel to the x-axis. What about if the rotation happens parallel to the y-axis or about the y-axis, either rotating about the y-axis or some other vertical line parallel to the y-axis? So what happens now? Well, we have our limits of integration. Let me move this up a little bit. So we have our limits of integration. In this case, the rotation is happening around the y-axis, right? So this is where we have the rotation. So the limits of integration are from 0 to k, because if you construct the shell is always constructed parallel to the rotational axis. And if this is our shell, then the thickness of the shell determines which variable we're going to integrate with respect to. So the thickness of the shell is along the x-axis, so it's going to be dx. So x is going to be the variable of integration, and that variable changes from 0 to k in this figure, right? So that's from where you have the limits of integration. So again, 2 pi times x, and that would be the shell radius here. Let's see, the shell. So the shell, the shell radius here. So that would be x. The distance from any point on this curve would be a distance x from the axis of rotation, right? So that's x. And then f of x, which represents the height of this shell, which is basically tied to this curve, right? If I were to draw this shell height here, the top or the height of the shell would be here, again matching the value of f of x on that curve. So the curve is the height of the shell. Everything in this integration should be in terms of x, because we're integrating with respect to the x variable here. Okay, so what happens if we're rotating with respect to an axis that is parallel to the y-axis? Let's say in this case, the line x equals -1. If we're rotating with respect to that, just as before, the shell radius this time would be this distance, which is x, plus the additional distance away from the y-axis, right? In this case, 1 unit. Never mind that it says x equals -1. That's where the line is. But the distance is x plus 1. Okay, so that's the shell radius. 2 pi, of course, here. The limits of integration are here. And then the f of x, again, once again, is the shell height, which is tied to every point, the y value or the height of this curve, which is identified by this function f of x. Defines the height of this any point on this line. Okay. So having talked about this, let's then move to solving our first example. I know this is the first example from this section, but if you read the book already, then you can jump right ahead and tackle this problem right away and see what answer you get. But if not, even if you haven't read the book yet, I hope you have read it. But if not, you can just, based on the discussion that we've had within the past 10 minutes or so, you can just go about solving this. So sketch the problem and see what solution you'll have for this. And then we'll compare the answers at the end. So take no more than 20 minutes. You'll probably need 10, 15 minutes for this, but no more than 20 minutes. Okay, so I'm assuming you've done that, and now you're back. It specifically says use the method of cylindrical shells to find the volume of the solid generated by rotating the region bounded by the given curves. These are the curves about the specified axis. In this case, they're specified rotate about the y-axis, which I've shown here. So we're rotating about the y-axis. Before even I draw the region that we're going to rotate about the y-axis, we know the shell is going to be constructed parallel to the y-axis, to the axis of rotation. In this case, the y-axis, right? So now let's begin drawing this curve. I'm going to draw these easier one first. So y equals 0. That's basically the x-axis, right? Let me use my thick Sharpie here. So I'm just going to thicken the x-axis a little bit, like that. So that's y equals 0. Then x equals 1. So that's a small number, so why don't I give myself a lot of space here? That would be good. So I'm just going to put the 1 here. So this would be like that. And this is that curve, x equals 1. And then finally we have to draw this curve. If you do this on your computer or graphing calculator, you'll see that the graph looks like this. It goes to one piece of it goes like this. Let me see if I wanna. Yeah, I wanna like that. It's an increasing functions in that direction. Like that. So this would be our y equals third root of x curve. So the region that is bounded by these curves, the y equals 0, x equals 1, and this curve, third root of x, is the region we want to find the volume of if we rotate it about the y-axis. So let me highlight all of this. Axis of rotation being y, and this is the region of rotation. Okay, like that. Like that. Okay, so we have to draw, the first thing is we have to draw the shell, the cylindrical shell. Rotation is with respect to the y-axis, so let me draw the shell parallel to the y-axis. So this is our shell. So I'm going to create this illusion that this is cylindrical on a piece of paper like that. Like that, right? So this is so as soon as you draw the shell parallel to the axis of rotation, you can quickly identify the shell thickness, right? This shell thickness, this is shell thickness, this is dx, or shell thickness. So the shell height tells us what the thickness is, which is along dx. So we already know the integration will have to happen with respect to the x variable. So that's the important part. And then also the shell height would be this distance. Let me mark that off as well. This is shell height. We have one more thing to identify, right? Shell radius. So the shell radius is the distance between from the center of the shell, so from here to the axis of rotation. So that distance. Like that. Okay, so this is shell radius. I think we've identified everything, and that's of course the origin here. Let me also identify that 0, 0. Okay, so now we can apply. By the way, I've drawn portion of this curve, third root of x. The rest of it we don't need, right? Because we're integrating over this region that is bounded by these three curves. These three curves, right? These three. So that's why I didn't draw the rest of this curve, but if I did, it would look like this. It would be like that, but we don't need this piece of that curve. Okay, it does continue on this side, but we don't really need that. Okay, all right, so having said that, let's apply the formula. We have the cylindrical shell formula, says that the volume would be equal to, by the way, the limits of integration is the distance from the axis of rotation to that point, which is 1, along the x-axis, dx. So it would be from 0 to 1, 0 to 1, 2 pi, right? That's part of the formula. Then which one did we say? Did we say shell? Radius of the shell. So radius of the shell at any point on this curve, or from this curve, radius of the shell, because these at any point would be the x, right? So this distance would be x. So 2 pi x, that's the shell radius, times the shell height. Shell height, we know it's defined by this curve and this curve. Oops, sorry, I was off the screen there. Sorry. So the shell height is defined by this curve mainly, but at that point where we have an intersection, x would be equal to 1. We know that. For this function, it would be third root of square root of 1 at that point. But at any point along this region we're integrating, the shell height is defined by that curve, right? So times, oops, I should be careful here not to be off the screen. So third root of x, and then of course dx. Okay, so now, maybe if I zoom out a little bit, it'll be better. Well, like that. A little more, like that. Okay, so we can integrate now. Let me move this up. So we have the volume equals, so let me rewrite this as with exponent, with power, as a power function. So we have x times x to 1/3 power dx. Of course, these powers get added. So we'll have 4/3, right? And I'll put the 2 pi in front times the integral from 0 to 1 of x to 4/3 power dx. Of course, this is a simple integral, so we know that volume would be equal to 2 pi times 3, so that would be 3 over 7 times x to 7/3 power, and then limits of integration from 0 to 1. Okay, so what do we have here? We have the volume equals 2 pi times, if we substitute for x with 1, we get 3/7. Substitute for x with 0, we get 0. So we get 6 pi over 7 as the volume of that object that is generated as such. Okay. All right, so we have that. Let us do another example. So here we have a region bounded by these curves. Y equals e to minus x squared, y equals 0, x equals 0, x equals 1, and we want to rotate that region bounded by these curves about the y-axis again. Okay. All right, so let's draw these regions, but before I do this, I want to remind you, please pause the video, write down your own solution, and then come back to the video after that. I'm counting on you to do that. Okay, so I'm going to draw these easy curves first. So we have x equals 1. Again, that's a small number, so I'm going to give myself plenty of room here and say that this is, let's say this is x equals 1. And then we have y equals 0, x equals 0. Y equals 0 and x equals 0 are simply x-axis and the y-axis respectively. So this line, and that line. And then, of course, we have that curve. If you use your graphing calculator or computer to graph this, you'll see that it's going to look something like this. And I'll try my best to do a good job on this, but I'm not sure. It's going to, on one side, it's going to look like this. On the other side, it's going to look like that. And then we don't, of course, care about beyond x equals 1, and we don't care about to the left of the y-axis, right, because of where the boundaries are. So what we care about here, and let me thicken this with my Sharpie, it's going to be from here to here, that region, and which is bounded here. Here. So this is the region we're going to rotate with respect to the y-axis. Like that. Okay. So I want to label these. So this is the boundary line y equals 0, and then also x equals 0, and that line, and x equals 1 we already have, and this one would be that curve. So where do I want to put that? I want to maybe put that here. Maybe here, y equals e to minus x squared. Okay, that's our curve. All right, so the rotation is about the y-axis. Therefore, the shell's height should be constructed parallel to their axis of rotation. So I'm going to draw my shell like that. Just like that. Right? Parallel to the shell height is now parallel to the axis of rotation. And I'm going to identify it as that. So this is the shell height. And then quickly we see that the shell thickness is here, this distance, which is parallel to the x-axis, right? So therefore, shell thickness, therefore the variable of integration is going to be x, or dx here, okay? And then, so we need to identify the shell radius. The shell radius is always the distance between the center of the shell and the axis of rotation. So let's draw that as well. Center of the shell and the axis of rotation. Shell radius. Okay, I think the other thing we want to determine here is that, well, we don't really need it, but it's nice to know where's that point. That's the point where x equals 0 on that curve, right? So if you substitute for x with 0, we get e to 0 power, which is 1. So that point, I might as well mark that. That point is 0, 1. Okay. All right. So now we have everything in front of us. We can go ahead and integrate here. And that point, by the way, is 1, 0. So let me also mark that 1, 0. All right, so volume, as the formula says, we're integrating with respect to the x variable, and that is changing from 1 to 0, so 0 to 1. Then we have 2 pi, and then the distance at any point on this curve from the axis of rotation, or shell radius, as this shell moves from here to here, along the curve being the height of the shell, that distance x changes from 0 to 1, right? So x would be that distance at every point along the curve. And then the shell height, once again, it would be this function. Shell height would be that function. At this point, though, the shell height would be equal to whatever point, at that point it would be 1 e to minus 1 squared power e to minus 1. So it would be 1 over e at that point. So the height would be 1 over e. It's immaterial, so I'm not going to write it down, but at this point, x would be 1. So e to minus 1 squared would be the height of that at that point, the height of the shell at that point. Okay? But it's immaterial. All we need is the curve. So I'm going to put that here. And then variable of integration, which is dx. Okay, so here, let me rewrite this or clean it up a little bit. So we have 2 pi, which is a constant. Let me put it in front, times the integral from 0 to 1, x times e to minus x squared dx. So here we have We could use maybe integration by parts, but there is an easier way also, because notice that if you take the derivative of this, right, if you take the derivative of this, you get minus 2x, right? And we already have a 2 here. Maybe I should have kept this 2 on the inside so it would be more obvious what this is. Why not? Let me do that, because I just noticed that it's better if I keep the 2 inside. I'm just doing this for the sake of clarity. If you see what I'm doing, you don't have to do this. You can just go from here. But for the sake of clarity, let me do this like that. So I just move this 2 from in front to inside of the integral here. So if you take the derivative of minus x squared, you get minus 2x, right? So the only thing that we need is just a minus in front to make that positive. So so we can do a easy substitution here, basically. Let u be equal to x squared. That means du would be equal to 2x dx, right? 2x dx. And then because we switched to u, a new variable, we need to recalculate these limits of integration. So if x is equal to 0, then u is also equal to 0. And if x, move this up a little bit, if x equals 1, then u would be equal to 1 as well. So the limits of integration didn't change. That's great. But now let's substitute in our new integral with these limits and with this variable u. So we have the volume equals pi times the integral from 0 to 1 again. Now instead of, notice 2x dx is just du, right? 2x dx equals du, 2x dx. So we can replace that with du, and e to minus x squared can be replaced with e to minus u power. So e to minus u power du. Okay? So if we integrate this, we're going to end up with minus e to minus u power, right? That's an easy integral here. Minus e to minus u power, and then from 0 to 1. Okay? So we have just a little bit more left to finish up this problem. So we get minus, if I write this with positive power, we get that, sorry, no, not u, but just e. So it would be e to minus 1 power, and I want to write it in positive with positive power, so minus 1 over e, and then minus substituting for u with 0, we get minus 1. Like that. I'm just double checking this. Yeah, it looks right. And then of course we have, what do we have? We have the volume equals pi times, if I rewrite this, so we have 1, that's positive 1, minus times minus. 1 minus 1 over e. Okay, like that. I hope this is starting to make sense. We just have to remember that the shell is always constructed parallel to the axis of rotation, and then that gives us the variable of integration, and then we have to determine the shell radius and shell height from that point. All right, let's do another example. So in this case, we have 1, 2, 3, 4 curves, and then we have rotation about the x-axis, right? So let's start with the easy ones first. Y equals 3. So that would be, let's see, 1, 2, and 3. So I'm going to draw a line going through that. So this is y equals 3. Then we have y equals 1. That would be through here. And this is 1, 2, 3. So it would be through that point here. Y equals 1. Oops, y equals 1. And then x equals 0, it would simply be the y-axis, right? So maybe I should thicken it a little bit. Why not, right? It will make it clear where the boundaries are. So that's that boundary, x equals 0. And I'm going to write that here, x equals 0. And then what else? Oh, we have this hyperbola here, so we have this hyperbola here, but given these boundaries, this boundary and these boundaries, so this curve has 2 pieces, right? Because let me grab a scratch paper here. So that, very quickly here, that's a hyperbola. So we can rewrite this as y equals 1 over x or x equals 1 over y, right? So, and because it's a hyperbola, then it's got 2 pieces, but we don't really care about the piece that is going to be off this way. I'm not going to draw that. We just need the piece that goes here. So let me draw it as best as I can. Hopefully it'll look good on the screen. So it should go something like this. Something like that. This will continue this way, this will continue this way. And just remember, the other piece we don't need. The other piece would be here. But we're not going to draw it. So that's all we need. And so the region that is bounded by all these curves, this one, that one, and this one, is right here, right? Right here. And we're going to rotate this region about the x-axis and determine the volume of the solid that this will generate. Like that. Okay. So I want to make sure that I need to also label this. This one, by the way, we can call it y equals 1 over x. Or x equals 1 over y. Okay, like that. So the axis of rotation is x, so we need to draw our shell parallel to that, right? So let's do that. If I draw my shell here, and also here, so that's going to be our shell height, right? Let's label that. So this is shell height. This is going to be shell thickness, right? That distance. So shell thickness. So the shell thickness is along which axis? It's along the y-axis, right? That thickness of this shell is along the y-axis. You can see it right there. So the variable of integration, it's going to be y. So we have to have dy in our integral. Do you see how important it is to sketch these? So that it makes everything clear. Shell height, and the next is shell radius, right? Which is the distance from the center of the shell to the axis of rotation. And I'm going to put that here on this side. From that point to this point. Maybe a little bit further, like that. And this distance. So this is so that is shell radius. Okay. So now that we've identified, I think, everything, just double checking, yeah, shell thickness, shell height. Let's write the formula for calculating this volume. So we have, you can see on the figure that the limits of integration will be from 1 to 3, right? From 1 to 3. So from 1 to 3 here. And then we have 2 pi. Then the shell radius at this point, so shell, let's see. So the shell radius in this case would be that. How do we want to? So that would be at any point along this curve, that would be y, right? The y value. For every point along this curve, the distance from that point to the axis of rotation would be the shell radius, and that would be y. That distance would be y, because it's rotation with respect to the x-axis, so I'm going to just put y here, times shell height. So shell height would be this distance. This distance would be, for this curve, it would be 1 over y, because that's along the x-axis, right? This distance from every point on this curve to the axis of rotation is x equals something, right? X equals what? X equals 1 over y, so we would prefer that here. So 1 over y dy. Okay, so limits of integration are taken from here, 1 to 3, 2 pi, and then y is the shell radius from the center here to the x-axis. That height is always y. And then 1 over y would be the shell height given by this value, x equals 1 over y, right there. Okay, so this is going to simplify things, because notice that this y and this y will cancel out. We end up with the volume going from 1 to 3, 2 pi dy. So this is simply 2 pi y integrated from 1 to 3. And then the volume is 6 pi, right? So 2 pi times 3 minus 2 pi times 1. So 6 pi minus 2 pi, that's just 4 pi. Like that. Okay. So again, drawing figures before we solve these is indispensable here. We need them. Let's do another example. So once again, I want to ask you to pause the video. You've seen several examples by now, so go ahead, draw the boundary enclosed between these two curves and go about solving the problem, and then maybe after 20 or 25 minutes, come back to the video and see how our solutions agree. Okay, and I trust that you've done that, and now you're back. So here, I'm going to start with the easiest curve, that one. I'm going to draw, this is just a straight line, right? Y equals 3, minus x plus 3. So, and I mean, right from here, we can get a pretty good idea of where the x and y intercepts are. So if we substitute for x with 0, y equals 3. So that would be 0, 3 would be that point. And then if you substitute for y with 0, x would be equal to 3. So 3, 0 would be the other point. So let's draw through those intercepts the straight line here, like that. Like this. So, like that. And I want to put on this line the equation that is associated with, like that. And so, and also let me label these points. We have 0, 3 here, and 3, 0, 3, 0 here. All right, so that was the easier curve. Now this one, this being a parabola, it's in standard form. So it's going to have a vertex, and it's going to have x and y intercepts. So let's find the intercepts for this one. So the intercepts for this piece, intercepts are, so if we take y as 0, we will find the x-intercept. So with y equals 0, minus 1 squared is just positive 1. 4 minus 1 is 3. So that would mean x equals 3. So that will give us the x-intercept for that curve as 3, 0. So good. So it's going to go through the same point as this straight line is going through. So then let's find the y-intercept. So if x equals 0, what do we get? We get y minus 1 squared equals 4. And then, so if we take the square root of both sides, we end up with y minus 1 equals plus or minus 2. And so this is going to give us, it's going to give us y equals 3 and y equals minus 1. So for this one, the y-intercepts would be 0, 3 and 0, negative 1. Okay, so the y-intercepts are going to go, it's going to go through that, and also this one. 0, so that point, and also this point. And notice this minus in front of this quadratic piece. This is just going to tell us, it's telling us that the parabola is going to open towards the y-axis this way, like that. It's going to go like this. So where's the vertex? The vertex is going to be 4. It's going to equal 4, 1. because this is already almost in a standard form. So this is y minus k. You remember we talked about this in pre-calculus. So, so here we have 4 for the vertex would be at point 4 comma 1, positive 1. And this is helping us establish that very quickly. 4 comma 1. So if I draw that, so let's say if this is 4 comma 1, that would be this point here, roughly this point here. Now I have to draw a parabola that goes through all these points. This one, and it's going to curve here, it's going to go through that, and so let me try. I'll do my best to make this as good as I can possibly do. So I'm just going to draw this easy piece first. So it's going to go from here through that. So that's one piece of that curve, like that. And another piece should go like that. So, like that. Okay, not too bad, I guess. Like that. Okay, so you can see the region that is bounded by these two curves, and this is x equals 4 minus y minus 1 squared. That region is right here. Right there. So we're going to rotate that region about the x-axis and calculate the volume of that. So that means, as you know, that the shell that we construct has to be parallel to the axis of rotation. That means my shell has to look like this. One end of it on this side, one end of it on that, like that. So this is our shell height. Shell height is parallel along the axis of rotation. I'm going to put here. So what is the shell thickness then? The shell thickness is along the y-axis, right? That means our variable of integration, it's going to be y. So this has to be dy. So this is shell thickness. And it's equal to dy. Right? That's dy. And then the shell radius is the distance from the center of our shell here, roughly here, to the axis of rotation. Like that. So that's the axis of rotation, the shell radius. Shell radius right there. We have the shell thickness, shell radius, and this, of course, is the shell height. Shell height. Okay. The drawing got a little bit cluttered, but it's okay. It's better to have it than not to have it. All right. So now let's set up the formula for calculating this volume. We have volume. So where are the limits of integration here? because we're integrating with respect to y, so we have dy here, so the limits of integration would have to be from this point, which has y value 0, all the way to that point where it has a value of y value of 3. So 0 to 3. Okay, and then we have 2 pi times the shell radius is, again, the height, let's see, or the shell radius is that distance, which will be, let's see, from any point on this curve would be the shell radius here. Let's see, like that. So at every point on this line and on this curve, the heights are going to be the same, right, for the shell radius. Whether you're here or there on that curve or on this line, the shell radius is not going to be different depending where you are on that curve or on this line. It's going to be equal radius, shell radius. So that's going to be y because the rotation is taken with respect to the x-axis. So any distance like that from the x-axis is just y. So times y. Then the shell height is a different matter because, so here we have, because we have a difference, we have two curves that one of which is on the right, the other one is on the left. So this curve, x equals 4 minus y minus 1 squared, is to the right and above this curve, right? So the order of, so we need to subtract this curve for this region. We need to subtract this region, this value, or maybe I should rewrite this. So let me quickly do that here. So from here, because the integration is happening with respect to the y variable, so let me write x equals 3 minus y, like that. But this curve, because it's above and to the right of this curve, then we need to write it like that. This distance, the shell height, would be that distance minus this distance, right? Any point on this curve has a distance equals to that from the y-axis. And we're taking the shell height, right? And any point on this line has a distance equal to that, 3 minus y, from the y-axis. So, because this is to the, but we're rotating this region about the x-axis, so we need to calculate the difference between that distance and this distance. And the curve that is on the bottom or to the left is always subtracted from the curve that is above or to the right of the other curve. In other words, what I'm saying is that we write this first, so 4 minus 1 minus 1 squared, all of that, minus the curve that is to the left of it, or below it, which is that, 3 minus y, dy. So notice that I had to rewrite this equation, or this curve was already in terms of y, x in terms of y, right? That's good because the integration is happening with respect to y variable. We have dy here. But this I had to rewrite so that it is also x in terms of y, because our variable of integration is y variable, right? So I had to rewrite that. So this subtraction is key because previously, notice that if I bring this back, well, maybe that won't apply. But in this case, the region that is bounded is the difference between that curve and this curve. And because that curve is above and to the right of this curve, we have to subtract the curve that is below from the curve that is above it. The order of subtraction in an integral region like that is always like that. So the region that is below or to the left is going to get subtracted from the region that is above or to the right. Okay, all right. So now that we have our integral set up, we can go about simplifying it and calculating it. Hopefully I can fit all of this on one page. So we have, let me put the 2 pi out here, 2 pi times integral from 0 to 3, and then we have y times all of that. So y times, I'm going to expand this. So we have 4 minus, expanding that, we get y squared minus 2y plus 1 minus 3 plus y, right? I just distributed this minus. All of that dy. So now I need to distribute this minus as well to this expansion. So we have 2 pi times integral from 0 to 3, and then y times 4 minus y squared plus 2y. Notice I'm distributing this. Minus 1 minus 3 plus y dy. And then, of course, there are things here we can combine. So minus 1 and minus 3 add up. They give us minus 4. And then this 4, they add up to 0. So that, this, and these 3 will cancel each other out. So we end up with the volume equals 2 pi times the integral from 0 to 3 of y times, what do we have left then? We have minus y squared on the inside plus 2y and y add up to 3y dy, right? And then, so we have, okay, so I need to distribute this y as well. So we have 2 pi times integral from 0 to 3 of minus y cubed plus 3y squared dy. Okay, so this is pretty easy integral to evaluate. We have the volume equals 2 pi times minus 1 over 4 times y to the 4th power, and then y cubed there plus y cubed and integral from 0 to 3. Okay, so let's substitute. We have 2 pi times 3 to 4th power, that's 81, right? So minus 81 over 4, so 81 over 4 plus 27 here, minus, if we substitute 0 here, we get 0 and 0, so 0 plus 0. And then, so this is just taking the common denominator. So we have 4, common denominator would be 4. So we have 108, let's see. 108, so yeah, 27 over, okay, so I think after simplifying, should get 27 over 2 pi. Of course, with this on the outside here, right? So this is after simplifying, and I want to verify that very quickly. So let me use a scratch paper here. So here we have 4 minus 81 plus 108 8, and so this will be 7. Yeah, so this would be minus 27 over 4 times the 2 pi out here. So this 2, so we end up with minus 27 over 2 pi. This would be plus. Yeah, 108 plus negative 81. So this would be positive 27 over 4, and then times the 2 pi, positive 27 over 2 pi. Okay, for a second, I doubted the solution that I have there, but it works out. Okay, so this is that. I hope this is making sense as we solve more examples. So let's solve another one. So here we have these 3 curves, and this time we want to rotate about this line, x equals negative 1. So this is the x and y axis right here. The rotation is now off any of the major axes. It's about x equals negative 1 line. Okay, so let's draw these curves. That one is an easy curve to draw, right? It's just going to go right there. It's going to be on the increasing function on the positive side. And also x equals 1. So if that's negative 1, so let me draw a line right through that. So this would be our x equals 1 line, like that. This is x equals 1. And y equals 0. That would be the x-axis. Maybe I should thicken it a little bit. Maybe like that. And then, of course, this curve right here, it would be something like this. Just an increasing function, like that. Okay, so the region we're integrating is bounded by all these curves, x equals 1, y equals 0, and this curve. And we're going to rotate this region about this line, x equals 1, and we're going to calculate the volume of the solid that is going to generate. So you remember, once you have the region, the first thing is draw the cylindrical shell, and the cylindrical shell height is always drawn, the cylindrical shell is always drawn parallel to the axis of rotation. So the shell is going to look like this. That's our cylindrical shell, like that. So the shell thickness is clearly that. So shell thickness is along which axis? It's along x-axis, right? So the variable of integration has to be dx. The shell thickness tells us the variable of integration. It's pretty important, dx. And of course the shell height and we also have to identify the shell radius. The shell radius is the distance from the center of the shell, this point, and the axis of rotation, which is x equals negative 1. shell radius. Okay, and I also want to put on this curve y equals a square root of x. Okay, I think that graph captures all the information we need. Yeah, it does. So let's set up our integral. And by the way, that point is 1, 0, right there. Okay, so the volume, it would be integral 2 pi from limits of integration, because we're integrating from this point to that point along the x for x, right? The variable of integration is x, so we have dx. The x is changing for this region. The x is changing from 0 to 1. So the limits of integration are 0 to 1 for that region, times the shell radius. Now, here something interesting happens, because if we were rotating about the y-axis, the shell radius would be that distance, right? Which would be just x, because we're calculating a distance from the center of this shell to the axis of rotation, and that distance is always x. If the shell was out here, x would be whatever that distance is from the axis of rotation. But now the axis of rotation is here. So the distance, the shell radius would be x, whatever that x is, plus 1. Now I know some of you might think, well, why not x minus 1? Well, because we're calculating this line is located at this position, x equals -1. That's where the line is. We need this information to draw the line. But when we talk about the distance or the shell radius, the distance is always positive. So x plus 1. If this was x equals -9, it would be x plus 9, the shell radius. If it was x equals -20, it would be x plus 20, just to represent the distance for this quantity, shell radius. So 2 pi times x plus 1, that's the shell radius. And the shell height is always going to be, whether the shell is here or here, anywhere in this region, the height of the shell is always calculated by this curve, right? Y equals square root of x, or right here. So at this point, though, the two curves intersect, which means this one and that curve and this line have the same value for the height of the shell. So the shell height would be represented by square root of x, and then, of course, dx. Okay? I hope you're seeing the connection between everything that is drawn and this symbolic form. It's very important. That's probably 90% of solving these kinds of problems. The rest is just easier stuff. So we have 2 pi times the integral from 0 to 1. I want to rewrite this in terms of a power function. So when I do that, right, let me do that. So x plus 1 times x to 1/2 power dx. Now I'm going to distribute. So we have the volume equals 2 pi times integral from 0 to 1. 1/2 plus 1, the powers get added, right? 1/2 plus 1 is 3/2. Plus x to 1/2 power dx. Okay. All right, so we have v equals 2 pi, and let's integrate this. 3/2 plus 1 is 5/2, and then divide by that, it would be 2/5 times x to 5/2 power, and then plus, that would be 3/2, so 2/3 times x to 3/2 power, and then 0 to 1. 0 to 1. Okay. All right, so let's substitute for x with these quantities, keeping in mind that we have this 2 pi in front. So that's just going to be 2 over 5 plus 2 over 3 minus 0 plus 0, right? When we substitute for x with 0, we get that. So then we have 2 pi times, so 15 being the common denominator, we have 6 plus 10, 16 over 15. And then, of course, we have v equals 32 pi, or 32 over 15 pi. Okay, so that's that. Let's do another example. So here we have two curves, and we want to rotate them, rotate the region that is bounded by these about this line, y equals minus 2. So again, we're rotating the region that I'm going to draw about an axis that is off the main axis, x and y axis, right? This is the axis of rotation. Okay, so let's draw the easy curve first, x equals 2. So that would be, well, before that, I want to ask you to pause the video, just reminding you that. I know I've mentioned this many times before. Please pause the video. You've seen plenty of examples, so you should be able to solve this all the way. If not, it's worth that you write down your own solution first before looking at the solution I have. Okay, please write your solution first. So I'm trusting that you've done that, and now you're back. So I'm going to start with the easiest curve. I'm going to draw that very quickly. That is x equals 2. And then this curve, that's another quadratic, or that's another parabola. It is x equals that, so it's a parabola that opens horizontally like that, and it's opening to the right because the coefficient of y squared is positive. If it was negative, like the example we had earlier, it would open to the left. But this is positive, the coefficient is positive, so it's going to open that way. And so the only question is where is, we should find the intercepts, so let's do that. So the intercepts here, how do I draw this? So it's just that, so intercepts. So if we substitute for y with 0, so if y equals 0, then x equals 1. So we have 1, 0 as one of the intercepts for that curve. And if x is equal to 0, then let's see, so we have, or x equals, so there are, let's see, there are, for this curve, if x equals 0, let's see, y would be, oh, there are no, so if you substitute for x with 0 here, y squared would be, y squared equals negative 1, right? So no, this is impossible, well, this would be, it wouldn't have any real solution, so no y intercepts. So this curve is not going to intersect the y-axis. And so where is the vertex then? The vertex, again, this would be x minus 0. And so the y, so x would be, the vertex of this parabola would be at 1, because it's opening like this. It would be at 1 comma 0. Just looking at that, because y, because let me use a scratch paper here. So we would have y minus k squared plus 1. So this is the, for the vertex, that's the value for x. And then because we have y squared, so k must have been equal to 0. K must have been equal to 0. So that means that the vertex would be at 1 comma 0 on the x-axis. So 1 comma 0 would be right here. That's the vertex, 1 comma 0. Okay, and this has to open like that. So the only question is, where would it intersect this line? We need that. We need that information because the rotation is about the this axis. So the shell would be parallel to that axis, and then we would need the limits of integration. So we do need to calculate where this curve intersects this line, and that's easy. We simply substitute for x with 2 and calculate the y values. So let's do that. How do I guess if I write it here, maybe. Let's see. Maybe here, I think I could fit it right here. So to find the points of intersection, let's call them, we have, so x equals 2, right? Because we want to know where that parabola is going to intersect this vertical line. So that vertical line is at x equals 2. So I'm just going to substitute for that. So 2 equals y squared plus 1. And this would be y squared equals 1. And this would be y equals plus or minus 1. Okay, so those points then would be, the points of intersection would be at 2, right? The line is at 2, comma, positive 1, and 2, comma, negative 1. These are the points of intersection along this line. So let me plot these 2 points. 2, comma, 1 would be somewhere here, I guess. If I draw that, it would be here. 2, comma, 1. And then 2, comma, negative 1. So that would be roughly here. Like that. And then I guess now I can draw that with my blue ink here. So one of this would look like that, and the other piece would look like this, like that. Okay, so now the region bounded by this curve, and that curve is clearly that middle section, right? So it would be here. All of that region. And because we're rotating this region about this y equals negative 2, line, so the shell has to be constructed parallel to that, right? So let me draw it here, maybe here. So that's our shell. Notice the shell thickness, right? That's the shell thickness. So the shell thickness is along which axis? It's along the y-axis, right? It's in the vertical direction, the shell thickness. So the variable of integration, it's going to be y, so we're going to have dy. Okay, and then what else do we need? We need the shell height and shell radius, actually. So shell radius would be that distance from the center of the shell, from here, the center of the shell, to the axis of rotation. So that distance here, like that. So that's shell radius, like that. That distance. And I think we have everything we need. And let me put on this curve here, I'm going to write this is x equals y squared plus 1. And it's nicely given to us because the integration is with respect to the y variables, and this is x equals y squared plus 1. So it's going to work out pretty nicely there. All right, so we can set up the integral now. And the limits of integration, it's going to be from, because it's dy, so along in this region, the y changes from -1 to +1, right? So that's why we needed those 2 points, -1 to 1. Those are the limits of integration. All right, so I'm going to write that here. Oops. I'm not sure if the connection got, but give me time, since my projector stopped all of a sudden. I hope that, oh yeah, it's still continuing, so I'm going to keep recording, guys, but give me time to get back on track here. I need to activate my dock camera because it went offline. And so document camera, so it's back again. And so I hope this is still recording. If you're watching this video at this point, something happened to the technology in the room. The projector screen went up suddenly in the middle of the session. So if it got interrupted, I apologize for that, but hopefully it's still capturing. And so this happened at 9:16 a.m. So I apologize for that, but there's nothing I could do about that. So continuing on, we have 2 pi integral from -1 to 1, and the shell radius. Remember that if we were taking the rotation about the x-axis, it would be just y. It would be that distance, that height would be y. But we have this additional 2 units of distance that we drop from the x-axis. So the shell radius is y plus 2. Again, it's supposed to be positive because it is a distance. So y plus 2 is the shell radius times shell height, which is identified by the difference again, right? Because here we have 2 curves. We need to calculate the difference. This time, the curve on the right is 2, right? X equals 2. So the difference between that and we have to subtract the curve that is on the left from the curve that is on the right. Inside of our integral, we need to subtract the curve that is on the left from the curve that is on the right. And that order is always the same when you calculate this integral of a shell. So 2 is the curve on the right minus this curve, which was given to us by this, y squared plus 1. So 2 minus y squared plus 1 dy. Okay, so please remember, this difference is always calculated with the boundary on the right minus the boundary on the left. The left or the bottom boundary, either one, in this case, the left boundary applies. The left or the bottom boundary always gets subtracted from the boundary on the right. Okay? All right, so now we can continue. We have 2 pi, minus 1 to 1, y plus 2. I'm going to expand and simplify this. So we have 2 minus y squared minus 1 dy, distributing that minus into that. And then we have 2 pi times integral from negative 1 to 1. Let me just put the simplified version here. Y, after distributing, we should have y minus y cubed. So this would be 2 minus 1 is just 1. I should have written 1. 2 minus 1 is just 1. But anyway, after that, we'd have, after we simplify, we distribute and simplify everything, we should agree that this is the result. And this is an easy integral. So let me write it here. 2 pi times, that's just 1/2 y squared. This is minus 1/4 times y to the 4th. This is plus 2y. And minus 2/3 times y cubed, going from, integrating from negative 1 to 1. Okay. All right. So the volume then is equal to 2 pi times, substituting for y with 1. So we have 1/2 minus 1/4 plus 2 minus 2/3 minus, then we have 1/2 again, and again minus 1/4, minus 2 here, and positive 2/3, like that. So after simplifying all of this and multiplying by 2 pi, we should get volume is equal to 16/3 pi. Like that. Okay. Again, drawing these graphs takes a little bit of time, I know, but without them, it would be much more difficult to get the answer right, or to know what we're doing, right? At least I feel that way. I feel that I need these graphs in order to tell me that I'm on the right track. Okay, so here again, we have this hyperbola again, and this hyperbola and this line, the region enclosed by these, we want to rotate them about the y-axis. So here is the axis of rotation about the y-axis. Okay, so I'm going to draw the easy part of this curve. Y equals 2, right? So I'm just going to draw a line through that point. So we have y equals 2, and so this hyperbola, we need to know where these two intersect, by the way, just like the previous one, because these two curves, because that will give us the limits of integration. So let's figure that out first. Oh, and this says use either the disk, the washer, or the cylindrical method to find the volume of the solid. So we'll think about that next. But let's figure out where this region is and where the limits of integration are first. So I'm going to substitute for y with 2 and calculate x. So let me do that here. So intersection points are, I hope I can fit it here. So we have 2 squared minus x squared equals 1. So this is going to give us 4, and then x squared equals 3. So x squared equals positive 3. So x equals plus or minus square root of 3. So the points of intersection then are at 2. Y, I should say square root of 3, comma 2, and minus square root of 3, comma 2, and y being equal to 2 here. Okay, like that. So that's just 2. That's my ink that just inadvertently I wrote that, but y equals 2. Okay, so these are the points of intersection. Let's find those. So this will be, so on this line, square root of 3, comma 2, if this is 1, so a square, and this is, let's say this is 1, this is 2, so that square root of 3 is slightly, it's 1 point something, so it would be here somewhere here, maybe with this point right there, and then also on the left side we'd have that right point right here somewhere. So 1, and then so apparently one of the pieces of the hyperbola is going to go this way. The other one is going to go this way. So then we want to know at which point that piece will intersect the y-axis. And that would be, so if we substitute for x with 0, right, the x-intercepts, or the y-intercepts, would be, if we substitute for x with 0, we get y squared equals 1, and that would give us y equals plus or minus 1. So here, so at, I guess, 0, comma 1, and at 0, comma negative 1, we have the y-intercepts for this hyperbola. So one piece, it's going to do this. Let me try to draw this as best as I can, like that. One piece is going to do that. Another piece is going to do that here. But we're not really concerned about the bottom piece, right? We're not concerned about that. That's the region that is bounded between this line, y equals 2, and this region. So I'm going to highlight that. Like that. So we have square root of 3 here, square root of 3, comma 2. And on this side, we have minus square root of 3, comma 2 for that point. So we're going to rotate this region about the y-axis and calculate the volume of the solid that this is going to generate. It seems to me that the disk method will perform just fine. So let's use that. They give us the option, disk, washer, or the cylindrical method. So I'd say we will use the disk method. We will use the disk method. Okay. All right. So the disk method, which we learned about in section 7.2 or the previous section, has a different formula. So it would be pi times f of x. So I'm just going to set it up like that. So we have, by the way, using the disk method, so our disk would look like that. So it would be like something like this. And then, so this is the, so that thickness is dy, or the disk thickness. So that this goes from this point to that point as we rotate that section about the y-axis. So the integration will happen along the, with respect to the y variable. Okay? So that means then, if that's the case, then I need to rewrite this curve in terms of, I have to write it as x in terms of y. Okay, so let's do that. I'm going to do that here. So if we have y squared minus x squared equals 1, then we can write x squared equals y squared minus 1, and then x equals plus or minus square root of y squared minus 1. Okay. All right, so the disk method, according to the disk method, then we have the volume equals, the limits of integration, by the way, because we're integrating with respect to the y variable, so we start at y equals 1, right, the bottom of this piece of the hyperbola, and we end here. That's the top of our region that we're rotating. So that's 2. So we go from 1 to 2. Pi times f of x squared. Right? This was the f of x squared. And then, so we get integral from 1 to 2 of pi times, we have that region, so where was that? This piece, x equals that, so times plus or minus square root of y squared minus 1 squared dy. Okay, just using the disk method. It's pi, not 2 pi, times f of x squared. Okay, so then we have the volume going from 1 to 2, pi times this squared will just get y squared minus 1, right? So y squared minus 1 dy, and then y would be equal to, if we integrate, we get pi times 1/3 y cubed minus y, going from 1 to 2. And the volume is equal to pi times, so 2 cubed over 3, so we have 8 over 3 minus 2 minus substituting for y with 1, we have 1/3 minus 1, like that. So after simplifying and multiplying by pi, we get the volume of that region, solid region, is equal to 4/3 times pi. Okay. All right, this was the last example. I hope this was useful to you. In addition, you have very good examples solved in the book, so please take the time to read those as well. We will go over examples in class using our classroom worksheet examples, so you'll see other examples in class as well as this. And I hope you come to me if you have any more questions. So thank you for persisting through the video. Have a nice day, and I'll see you again next time.